Alright guys, so we are looking at section 2.1 part 2. Today we're going to be starting to talk about the limit definition as a way to find the derivative of a function. So when we're doing the derivative, then we're going to be finding the slope of the tangent line to the curve at any point. That's important that you understand. Last night's homework was all about finding the average rate of change. The derivative finds the instantaneous rate of change. It tells us the slope. That's the rate of change. Slope is rate of change at one point. See, a tangent line just means that it is at one specific point. So here's what the derivative can tell us. Let's say I have this function like this. Maybe it looks like that. Suppose I want to know what's the slope right at that one point. There's no other math where you can do that. Because to find the slope at one point, you have to have a different method. Up to now, we always had to have 2 points. So like I might have that point that I'm given, and then I would have a point down here. Now we could find the slope, right? Or the average rate of change. But if I wanted to find the slope right there at the red dot, I have to use calculus. And the method that we use is called differentiating, or finding the derivative. When you get into college, you're going to see all these different symbols that are associated with differentiation. One is f prime of x. That prime symbol means derivative. Another way they write the derivative is dy dx. Another way is y prime. Or they can say d dx of f of x. So our limit definition is right here. To find the derivative, we have to do the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. We can also do the same formula, but instead of using a delta x, we can use an h. It's just that some colleges, they use the delta x notation, and some college professors use h, so I'd like for you to be familiar with both. So right now, that probably doesn't mean much to you. You're kind of like, what is that even doing? So let me come back over here to this piece of paper and show you. So if I'm trying to find the slope right here at this red dot, I want another point that's very close to it. I'm going to pick one just like right there that's even closer than the other one. So if I have a function, and my function is f of x could equal anything. Well, right here at the red dot, my point would be x, comma. How would I find the y value? What do I do to find the y value? If I had some function written here, what would I do? Plug it in, right? So this point is actually x, f of x. Another name for f of x is just y. Well, this point right here is very close to it. So I'm just going to say I moved over a certain amount. So this point right here then is going to be just x plus delta x. I don't know specifically what it is, but I just moved over a very small amount, just a delta x. Delta meaning the change in x, just a tiny bit. So what would the y value be then for this function? What would I always do to find the y value? Right, so this point is now f of x plus delta x. So yesterday when we were finding the average rate of change, what did we do? We found the what? Y minus y over x minus x, right? We found the slope. So if I want to find the slope between these 2 points, I can say that slope is going to be y sub 2. See how this y right here is f of x plus delta x minus, what's my other y value? All over this x, which is x plus delta x, minus my other x, which is just x. So this would now simplify to f of x plus delta x minus f of x. And what's the bottom just going to be? Delta x. Now, here's where the theory comes into it. If I want to know the slope at this one point, rather than for these 2 points, how far away should those 2 points be? Should they be 1 unit away, 2 units away, 0 units away? How far apart should they be? If I'm trying to find the slope right here, what would delta x really need to be to make it so this point is truly right there? 0. Delta x has to be 0. But would I be allowed to say delta x is equal to 0? Why am I, I'll tell you the answer to that. We're not. Why can I not say that delta x equals 0? What would happen to my formula? Well, if I put in 0 for delta x, what would this now turn into? Just f of x minus f of x. What is that? On the bottom, what would I have? What do I have to do? Yeah. So what that means then is I'm not allowed to let delta x equal 0. I have to call it a limit. I can't say delta x equals 0, but I can say delta x is getting infinitely close to being 0. Okay? That's where this formula comes from. I mean, anybody could have figured out this formula, but it wasn't until the mid-1600s that calculus was even born or studied. There were 2 mathematicians. Leibniz was one of the mathematicians, and the other one was Sir Isaac Newton. And they kind of like developed calculus at the same time. Some people give Newton all the credit. Other ones now give Leibniz all the credit. But at the time, Leibniz was blamed, or he was accused of actually having plagiarized the work of Sir Isaac Newton. So when he died, he actually died destitute, and no one, really respected him at all. But now when scholars go back and look at their work, they see that it was so different that it was almost just coincidental that they both happened to discover calculus at the same time. They actually corresponded with one another. Back then, of course, they couldn't text what they were thinking. So they were always sending these letters back and forth and like talking about what they were thinking. But I don't know. There's a lot of controversy. Maybe someday we'll do a math history project where you look that up, because it's very interesting. You guys are going like, no, that's okay. That was enough information about the history of calculus. All right. We'll stop with that then. So anyway, back to the 2000s. This then is how we are going to find the best estimate for the slope at one point, is this right here. Okay? So, back over here. So some of those early mathematicians, they were always using this delta x notation. And then as calculus kind of went further on, people are like, I hate writing delta x over and over and over. So then people just said, what's a variable we don't use very often in math? And they're like, let's just call it h. So do you see how these are the same formulas? One's just delta x and one's h. So I'm going to go back and forth using delta x's and h's. All right. So we're going to try our first derivative. This is big time. Remember how I told you there's 3 parts to calculus: limits, derivatives, integration. Those are the 3 main topics. So looking at this, f prime of x is going to be equal to the limit as delta x approaches 0. I'm just writing this whole thing. I've got this. Now I have to do this. So what is f of x plus delta x? That means in this problem, wherever I have an x, that x has to get replaced with x plus delta x. So doing this right here is 5, do the replacing, minus 4. Now I have to do minus f of x. What's f of x? All right, so I have to do that. All over delta x. So now simplifying this, I have to distribute that 5. I get this. Now we have to see if anything would simplify. Well, I have 5x minus 5x. I have negative 4 plus 4. My whole goal is to plug in 0 for delta x, but if I do it right now, I get 0 over 0. I have to do a little more work. I'm left with 5 delta x over delta x. Remember, delta x just means the change in x. It's just one variable. It is not 2. It's not delta times x. It's just one variable. What can we do right now then? Cancel these. So f prime of x, our first derivative we've done, is just 5. What did I say the derivative is the same as? Slope. What's the slope of this line? We didn't even have to do any of that work. I wanted an easy problem. From now on, if you see a linear function, you should immediately know what its derivative is. Yeah? Question? No? All right, let's try the next one. Y prime. See, look, guys, this means the same thing. This is saying find the derivative of f of x. Find the derivative of y. Okay, so here we go. Y prime is going to be equal to the limit. This time I'm going to do h's. Remember I said I'm going to just switch back and forth. I'm going to do h's now. It means the same thing. H is approaching 0. I have to do f of x plus h. So wherever I have an x, I have to replace it with x plus h. Now what would I write? Minus what? 2 over x. All over what? H. When we're doing limits, I want to just substitute in, but I'll get 2 over x minus 2 over x over 0. I get 0 over 0. Do more work. So, what shall I do with this then? Does anybody remember, Alex? Good job. That's the fastest way to get this simplified. In the numerator and the denominator, multiply by the common denominator. Do I multiply out on the bottom? No, never right here. Only where it's going to be helpful, which is on the top. So I distribute this. When I do this, I'm going to have this in the numerator, that denominator, those cancel. I just have 2x. When I multiply these, the x's cancel. I get minus 2 times x plus h. We do not multiply out the denominator. Am I allowed to cancel these x plus h's now? No, these are terms. I have to simplify first. So now I've got 2x minus 2x. That's 0. So I have negative 2h over xh times x plus h. Now I just have multiplication in the denominator and multiplication in the numerator. Once I have it down to all multiplication, all factors, then I'm allowed to do canceling. H divided by h. So now my problem becomes the limit as h approaches 0 of negative 2 over x times x plus h. My goal is to plug in 0 for h. Because once I do that, I can stop writing this limit over and over and over. Am I allowed to plug in 0 for h now? What am I going to get then for the limit, or for the derivative as well? Negative 2 over what? X squared. And that's going to be the formula that will tell me the slope or the rate of change at any given point along this curve. So if I wanted to know the slope at x equals 1, I plug in 1, and that's the slope right there. Okay? Alex?
Do you need to start the limit?
Personally, I don't care, but just be aware when you're in college, I've had professors who would take off for that because it's truly not a correct notation, but I'm not going to be too picky since this is like your introduction to calculus, so I'm not going to be picky. All right, so now it says find d dx of g of x. What's that saying? Just find the what? Derivative. Okay, so to find that derivative, it's going to be equal to the limit. Which do you guys like using, the h or the delta x? The Yeah, me too. I'm going to use the h. Sometimes I'll forget. I'll probably go back to delta x because I always had to use delta x, so I tend to go back to that. But all right, so using our formula, we have to do f of x plus h. So I have to take my function, wherever I see an x, I have to do x plus h. I have to cube it and add 2. Then I have to do minus f of x. Make sure you put that in parentheses. Then it's all over h. I have to cube this out, this binomial. Do you guys know how to cube out a binomial quickly? Alex, do you remember?
I'll do the x plus h, and then I think that's like x squared minus and then plus.
Okay.
It's like a root formula.
Yep. I'm going to show you 2 ways to do it. One way is, if I want to cube this out, I have to do x plus h times x plus h. I just want you to watch this for a minute and see which way you like better. So I have to multiply these. I get x squared, that's xh, that's xh. Oopsie, nobody can. Sorry. Secret way of doing it. So when I do this then, and then I have plus h squared. That's what I get when I multiply the first two. And now I have to do times the last one. So now I have to FOIL all this out. You guys see what I'm doing there? Just FOILing it all out, combining like terms. These are like terms. These are like terms. And that. This is the answer when I do that. Now, it's a bit of a pain to do that. Those of you who were in Honors Algebra 2, I know that you learned this as well. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Pascal's triangle. Good old Pascal. Yeah. So what he told us is, if I'm trying to raise something like x plus h cubed, then the pattern, the coefficients are always going to go 1, 3, 3, 1. So I know it's going to go 1. I take my first one, and it's going to have to get cubed. Every time the total power has to be 3. So now I go to my next one. My next coefficient has to be 3. This now has to go down, squared, and I bring in the h. I go to the next one, it's 3. The x's have to go down by 1. The h powers have to go up by 1. My last coefficient is 1. The x has to go away completely, and the h has to get cubed. I prefer to do this because I can just memorize that, and I'm not going to have to do all of that, which I do not enjoy. How many of you remember doing that a little bit? All right, great. Okay, so now I can do my replacing here. So sometimes in math things just seem familiar, but it's like, been a while, which I understand. But once you kind of see that pattern, it's going to save you a lot of time. All right. So now we're going to look for some things to cancel out. If they don't, then we made some mistakes because we can't plug in. We get 0 over 0. Those are 0. Those are 0. So we have all this stuff left. I'm going to just jot that stuff down. And I would like to plug in 0 for h, but I still can't. So what are we going to do in the numerator? What does every term have in common? H. So I'm going to take out an h. See, I really should be writing limit, but I'm getting writer's cramp from writing it so long. All right, so now my h's can cancel. And I'm trying to plug in this h is equal to 0. Can we plug it in now? Plug in 0 for h, plug in 0 for h? We can, can't we? So that means then that the derivative of g of x is equal to, what do I get when I plug in those zeros for h? 3x squared. That's our derivative. So that's going to be the function that's going to tell us the slope at any given point. It's going to tell us the slope at 1, at -1, at 3. Let me show you something here, guys. Do you know what x cubed plus 2 looks like? I hope so, but look, here's what our function looks like right here, okay? I could now use this formula. So if I plugged in, say, -1, -1 squared is 1 times 3 is 3. It tells me right there at -1 the slope is 3. That's what it's doing. It's telling me the slope everywhere on here. What would you think would be true of the slope at, say, 4? See right here at 4? Can you see how steep that slope would be right there at 4? Plug in 4. 4 squared is 16 times 3 is 48. The slope is 48 right there. Very steep slope. Kind of almost like a vertical line. All right, let's go on to the next one. Toughest one, but we're going to stop here. Find dy dx, that's another way of saying finding the derivative. So, dy dx is going to be equal to the limit as h approaches 0. Everywhere I see an x, I replace that with an x plus h minus f of x. That's going to be our first step. Does anybody remember when we were doing limits and we had radicals and we're trying to plug in 0 and what we would do then to solve this? McKenna? Yep, the conjugate. And I'm kind of running low on room. Put another piece of paper out here. I have to do that in the numerator and the denominator. A lot of people miss it because they forget to multiply by the denominator. Now, on the denominator, though, I'm never going to multiply that out because it's just going to get worse. I need things to get better, not worse. So dy dx then. So I have to FOIL this out. First times first, the radical just goes away. What happens anytime we multiply conjugates? What happens to the outers and inners? They always cancel out. There's no sense even doing them. Minus, if I multiply radical x plus 1 times radical x plus 1, that's just x plus 1. That's the important thing right there. What do you think people forget to put? Parentheses. Must be there. The bottom, don't forget that you still have all this stuff. Most people just forget, like I said, to put that in the denominator. All right, now I'm done with that. Okay, so now I'm going to have that limit. I'm going to simplify this. So this is going to become negative x minus 1 when I distribute it. So I have x minus x, that cancels. 1 minus 1, that cancels. So what do I just have left in the numerator then? Just... what is it, guys? H. What should I do now? Yep, cancel out those H's. I have a 1 left on top. My whole goal is to be able to plug in 0, and I can now. So I have a 1 on the top. If I plug in 0 here, I'm going to have a radical x plus 1, because that's 0, plus another radical x plus 1. What do I get if I add a radical x plus 1 plus another radical x plus 1? 2 radical x's plus 1. Okay, and that's our derivative. That's the formula that's going to tell us the slope at any given point. All right, feel like you can do that kind of thing? All right. Fun times. I promise derivatives get better after today. Today's that introduction day where it's just kind of a lot of work. All right, so here's the thing. I have this worksheet for you. I'm not going to make you do all of it. I'm going to circle some problems and I'll... So I want you to do 1 and 2. You should be able to do those very, very quickly. I want you to do number 4. Let's do number 6. I've got to do 7. and 9. I'll say those again. We're doing numbers 1, 2, 4, 6, 7, and 9 on the worksheet. One and 2 should go pretty quick. No, not on 1 and 2, but you should